Hey everybody, thanks for tuning in, and today I'm excited to talk to you about some EIGRP. We're going to cover all kinds of fun stuff like the feasibility condition, feasible successors, database manipulation using offset lists, so on and so forth. First, we'll go over a couple slides with important concepts and definitions. Then we'll jump right into the lab on an iOS system and put the offset list into practice. At the same time, we're going to learn about how to decipher some show outputs, who and why is a feasible successor or not. But to understand this, you should already have at least some basics of EIGRP down. Basically, you just need to know how to implement EIGRP in a network. You'll come away from the video with a better understanding on how to read the EIGRP topology database and how to use offset lists to manipulate the EIGRP topology database. So EIGRP, here's a few basic facts about it. Not going to go too far in depth into this because, as I mentioned, I expect you to already know at least some basics of it. What I will get more in depth on are the definitions in the next slide. So these definitions are some of the most important terms you need to know about basic EIGRP, especially to have this video click. You might want to pause here and take these down in your notes if you don't know them already. We'll need to refer to them later, so it might be helpful to pull them up if you need to, maybe take a screenshot. The most confusing one is probably the feasibility condition. I'll talk about that a little bit right now, but before we get too far into it, we'll look at an example topology in the next slide. So successor route. This is the route with the lowest path metric to the destination. Basically, this is what a router in an EIGRP system has determined as the best path to a target network. A successor refers to the next hop router for that successor route. So the next hop along the path that the router has determined as the best path. Feasible distance. This is the metric value for the lowest metric path to a destination. I'm going to go over reported distance and we'll come back to this in just a second. So the reported distance. This is the distance reported by a router to reach a destination prefix. This value is the feasible distance for the advertising router. So you'll have a router, right? And it'll calculate what is the metric to reach a certain destination. It'll advertise that out to the next router in the EIGRP system. That's your reported distance. So I'm router 2, and I know it costs me, say, $20 to get to, the network I'm trying to get to. It costs me $20. I'll go to the next router and say, hey, I can get to X network. It costs me $20. This is the reported distance. If I'm the router who just got that advertisement and I say, oh, he knows it costs him $20 to get to that network, but it costs me $10 to get to him, that means my feasible distance is $30. Obviously, it's not dollars in routers, but anyway. Moving on to the feasibility condition. Condition stating that for a route to be considered as a backup route, the reported distance received for that route must be lower than the feasible distance calculated locally. This logic guarantees a loop-free path. This is probably the hardest one to wrap your mind around. When we get into the next slide and you pull these definitions up to go along with it, it'll all make a lot more sense. But basically, say you have two paths to a network. We just went over reported distance and feasible distance. So I have two paths to a network. I know one is the best path, and I know my feasible distance. So say my feasible distance from the last one, I said it was $30 to get to network X. Now another router is telling me, hey, I know how to get to network X too. In order for me to consider that route as a feasible successor, which you see below is a route that satisfies the feasibility condition and is maintained as a backup route. So in order for me to say, hey, this is a viable backup route I can store in my database, the reported distance that I got from the advertising router has to be lower than the feasible distance I already have. So I already have a feasible distance to network X for $30. As long as whoever's telling me else they can get to network X is $29 or cheaper, I'm gonna say this is a useful route for me. I'm gonna keep that in my mind as a backup. If somebody comes and says, hey, it cost me $30, it cost me $31 to get to network X, I'll put it in the database, but I'm not going to consider that as a backup route. Let's go to the next slide, so it's not just me rambling and we have a picture to make sense of this. So in this topology, we're looking at this from the perspective of router 1 in the top left, and we're saying that we want to reach the 10.12.1.0/24 network over here. The dotted green line represents our successor route. The feasible distance would be 3328, which is the sum of each metric to reach the destination from router 1. The reported distance received by router 1 from router 2 would be 3072, or 256 plus 2816. Router 2 is our successor. This is the first hop router along the successor route. So router 2 would be called the successor if you're looking at this from router 1's perspective. The red dotted line represents our feasible successor route. Remember that this is a backup route maintained in the EIGRP topology database as a viable backup, a feasible successor. This feasible successor must satisfy the feasibility condition in order to be considered as a backup. One more time, the feasibility condition states that for a route to be considered a feasible successor, the reported distance must be less than the feasible distance calculated locally. What does all this jibber jabber mean? Feasible this, feasible that. So let's analyze. We know that the feasible distance for router 1 to reach our target network 10.12.1.0/24 is 3328. We know that the reported distance for our feasible successor route would be 2816 because that's the only other metric along the path. If we're looking at this top link here, the only other metric to get to this network is 2816. So when this router here, the final router in the line that I didn't label, it's going to advertise to router 1. Router 1 is going to receive a reported distance of 2816. Because that reported distance through the top link would be 2816, which is less than 3328, it satisfies the feasibility condition and is installed in the EIGRP topology database as a feasible successor. So that's what it means when it says it must be less than the feasible distance calculated locally. We already knew that our best path metric was 3328. And since 2816, the reported distance of the advertised route is less than our current feasible distance, we can install it as a backup. Now I know it might be kind of feeling like this right now. That's how I felt when I first was going over this stuff. At first, understanding this is it's almost like trying to read some legal documentation or something. I don't know if you've read it, but it's like, sub provision A, section D, for section 32.1AB, notwithstanding the subjugation of Article 59. You get the point. Some of those sentences are pretty long, Just copy down the definitions, do some searching to check out some more topologies with labels, and it'll all eventually click. I don't know if it happens to you, but it happens to me that I had to read the definitions very slow, very many times before it really started to click. And as always, get in a lab. Packet tracer will do if you don't have something else. And look at some of the outputs. Find the show commands to look at the routing table. Just learn how to decipher some of that stuff, which we will do in a few minutes here. But now that we understand the feasibility condition, successors, all this kind of stuff, we can examine an interesting topology, and then what we'll do is manipulate the EIGRP process using what's known as an offset list. Let's look at the topology. So when I read the definition of the feasibility condition and it states that it guarantees a loop-free path, I was kind of confused, and I designed this topology to illustrate my confusion. So let's look at this from the perspective of router 2, saying that we're trying to reach 10.4.4.0/24. All these routers are configured in EIGRP Autonomous System 12. All the links are the same bandwidth, speed, delay. Everything is kind of equal, if you will. So we can tell by looking at this, the ideal path to get to our target network would be from router 2 to router 4 and then, whoops, and then to our target network. But there's another path, right? We can go from router 2 to router 3 to router 4. There's no loop in this path, so it should be considered a feasible successor route, right? Well, it's not considered a feasible successor because in this case, the metrics don't add up and it doesn't satisfy the feasibility condition. The super interesting thing about the feasibility condition is it's not perfect. So what I mean by that is it can always guarantee that a route with a loop is not considered a feasible successor, but it can't guarantee that a route without a loop is considered a feasible successor. Given all of that, how could we configure router 2 in a way that the path through R3 is considered a feasible successor? This will, lower our convergence time because it's ready to go into the routing table right away should the link from R2 to R4 fail. And it's just interesting. So rather than talk about it, let's jump right in the lab and we'll find out. All right, so here we are in the lab. Gave you the spoiler already. Route 3 is not a feasible successor. How can we verify that though? So the command you're going to want to use in this situation is show IP EIGRP topology. So when we look at this, we see that 10.4.4.0, it looks like there's only one path. If you remember, I briefly mentioned before, all of the links are stored in the database, but it's only going to show you your successors and your feasible successors if you issue this command. If you want to see everything, you can do show IP EIGRP topology all links. So when we look at here, we can see that there is actually two paths to the network. But why is the path through 10.3.2.1 not considered a feasible successor? Well, it's because it doesn't satisfy the feasibility condition. So one more time, just to try to repeat it, repetition is key. The feasibility condition states that in order for a route to be considered a feasible successor, the reported distance received must be less than the feasible distance calculated locally. Well, let's look here. When you're looking at this output, right, this is your metric, this is your reported distance, and that's, obviously received from the other router. So our feasible distance to reach this network currently, the metric for our best path, is 307,200. Well, what's the reported distance from that other router, router 3? It's 307,200. So does that satisfy the feasibility condition? No. That's why it's not installed. How can we manipulate this? Well, you're in luck because I've got an answer for you. Hope that was a sneak peek to variance we'll talk about in a minute. Basically, what we can use here is a metric offset list. So an offset list is a mechanism for increasing incoming and outgoing metrics to routes learned. Optionally, you can limit the offset list with either an access list or an interface or both. An offset list is preferred when you want to narrow the scope of your influence on the metric to a particular path being advertised. So maybe you have additional routers connected and you don't want to influence any other paths originated by any other routers or maybe even any other networks. This is when you would use an offset list. It's worth mentioning that yes, you could manipulate something that EIGRP uses, such as the bandwidth or the delay. But if you do that, if you manipulate the bandwidth or delay for an interface, you're now affecting any other process on the router. So you might be affecting quality of service or OSPF or something like that. And also you're gonna change the metric for all paths to all networks learned on that interface where you make the change. So it's really not a preferred way to do it. So an offset list adds offset to incoming and outgoing metrics to routes learned. How do we do it? How do we do it? How do we do it? I'm going to tell you. Here we go. It's actually pretty easy. So the first thing that you're going to want to do in the router is go into configure mode. Then we'll create the access list. Can't type access list. And we're going to identify the network that we want to influence here. So it's 10.4.4.0/24. And we want to identify that one, so we'll permit access list 99. What is going on here? I guess we can just, yeah, there we go, access list. So there we go. Now we have our access list identifying the network. Now all you have to do is come into your EIGRP process, and we'll use the offset list. So offset list, access list is 99. We want to affect this for routes coming in. We're going to modify it by literally just one, because that's all we need to make this a feasible successor in this case. And this is coming in E01. So what this does, it says reference the access list 99, which identifies our network here, coming in this interface E01, and offset the metric by 1. So we'll go ahead and we'll do that. Now I may need to clear the neighborships here, but if we do show IP EIGRP topology, so let's wait a second for dual to calculate again. There we see dual. We got an update in our EIGRP process, dual recalculated, and it still doesn't show. So what I'm going to do is clear IP EIGRP neighbors. We'll wait for them to come back up. Okay. And now we can see that both of those paths show up with just our standard command. So that lets us know that this is now considered a feasible successor. If you look, our metric is changed by 1. Now our reported distance received is less than the feasible distance, so we have a feasible successor. But let's look at the routing table, right? For this, to get to this network, we still only have one path. Well, yeah, that makes sense because it's not an equal cost path, so it's not automatically installed. One of the cool things about EIGRP is that it provides support for unequal cost multipathing. And it does this through use of the variance command. This is what kind of popped up earlier. So variance is used to allow for unequal cost multipathing in EIGRP, and it consists of the following things. So you have an EIGRP variance multiplier, and this variance multiplier helps you arrive at or calculate the variance value. So the variance value is the metric for a route multiplied by the EIGRP variance multiplier, the feasible distance. So any feasible successor with a metric less than the variance value is installed in the routing information base and used in unequal cost multipathing. So if a feasible successor has a metric less than the current feasible distance multiplied by the variance multiplier, it's going to then be used in unequal cost multipathing. But once again, long sentences, bunch of words, maybe kind of confusing. Actually, it's really simple. Let's take a look at this. All we have to do is do variance. We're going to use a value of 2, right? So if we look at this, we see that we have 307,201. I'm famous for being bad at short math, so multiplying that by 2, 614,402. Now, we know also that our metric for this other route is 332,800. Is that less than this value here? Yes, it is. Therefore, it's going to now be installed in the routing information base and used in unequal cost multipathing. So we'll do show IP route. Now we can see that we actually have 2 paths here, and this is different than before. Before we only had 1, so now we have 2. We're unequal cost multipathing through both of these paths here, and if we do show IP route 10.4.4.0, we can see that we have traffic share on these 2 routes. So using the variance command, we've now implemented unequal cost multipathing. In conclusion, I would just like to thank you for watching. I hope you made it all the way through. I hope it's been informative. And basically what we did is we used an offset list to manipulate the metric for a route we learned in order to force another route to be installed in the database as a feasible successor. And then we used the variance command in order to allow that new feasible successor route to be used in load balancing, even though the costs are not equal. So pretty cool. And I don't know how useful this is anymore on the exams. It looks like they kind of are less heavy on configuration in EIGRP, but maybe this will be useful in your troubleshooting or in your life. And I just think it's interesting. So once again, thank you for watching. Let me know what you thought in the comments. Give a thumbs up, all that fun YouTube type stuff, and see you in the next video.